So our next speaker is sorry, Josh Hutton, I think. And he's here to talk about instruction scheduling for the GPU on the GPU. Josh performed this research as an undergrad research assistant at Sac State. He'll be attending UC Davis as a PhD student this fall. This work introduces a technique for parallelizing a precise instruction scheduling algorithm on the GPU based in intelligent search techniques. We believe that going forward, work that makes compute-intensive compiler techniques feasible like this will be developed and continue to meaningfully expand the menu of compiler optimizations and techniques used and available. Please take it away.
All right, thank you for the introduction. Hello, I'm Josh Hutton. I'm a co-author on the paper Instruction Scheduling for the GPU on the GPU. To give some background to our problem, register pressure-aware instruction scheduling is an open problem in code generation. It is NP complete, and because of this, current production compilers generally use greedy or heuristic solutions to approach this problem. We have implemented an intelligent search algorithm to run on the GPU. The main issue with instruction scheduling is in balancing register pressure with instruction level parallelism. This is especially important for a GPU target, where RP determines occupancy, the number of thread groups that can run together in parallel. Additionally, the GPU is an in-order processor, so there's no hardware scheduler like on most x86 CPUs to undo the scheduling that we're doing. For our scheduler, we tackle this issue by using a two-pass approach. In the first pass, we seek to minimize RP and maximize occupancy. To do this, we entirely ignore latency. We then take the highest occupancy schedule found in pass 1 and insert stalls into it in order to satisfy latency constraints, and then try to maintain the best occupancy we found in pass 1 while minimizing schedule length. The algorithm that we have chosen to construct these schedules is ant colony optimization. ACO is based off of how ants behave in the real world. Ants will wander around randomly looking for food, and once they find it, they'll begin to release pheromones and then wander back to their colony. Future ants will follow the pheromone trail to look for food, mostly, but the ants will occasionally veer off the path and then back on, which leads to the pheromone trail becoming shorter over time. In order to apply this technique algorithmically, we simulate the deposit and decay of pheromones using a pheromone table. This is an n by n table, with n being the number of instructions in the region, containing links from every instruction to every instruction. We'll deposit pheromone based off of the best schedule in each iteration and use the pheromone table to guide schedule construction. In our algorithm, we compute an initial schedule using some heuristic and initialize the pheromone table with that heuristic schedule. We then launch ACO on the GPU, where each thread represents one ant constructing a schedule. Thousands of ants will construct their schedules in parallel, and then we will select the iteration winner based off of RP for pass 1 and RP and ILP for pass 2. We use that iteration winner to update the pheromone table, and if that iteration winner is better than the global best schedule, we will update the global best schedule. This will continue until we reach a certain number of iterations of ACO without improvement. The ants construct schedules one instruction at a time. The ants choose instructions from their ready list, which is a structure that holds all instructions that have had all their dependencies satisfied. We then assign each instruction a score, which has a component based off of a lookup into the pheromone table, as well as a component based on whatever heuristic we're using. After we have all the scores, we then choose to either exploit the best known option so far or explore a less proven path. We exploit by selecting the instruction with the maximum score at the current moment in scheduling, and we explore by randomly selecting from all currently ready instructions, but we give a greater probability to selecting instructions with higher scores. Here's a simple data dependence graph that I'll walk through in order to give an explanation of how ACO works. In this example, we have 7 instructions. If every instruction defines a register, and the bottom instructions E, F, and G all use 2 registers from the instructions directly above them. The numbers next to each arrow indicate latency. However, we're going to immediately ignore those latencies for the first pass. In our actual algorithm, we'll have thousands of ants running in parallel for multiple iterations, but for this example, we're only looking at 2 sample schedules and 1 iteration. Ant 1 has selected 4 instructions that all define a register and use none, instructions A, B, C, and D. So after scheduling these 4 instructions, the register pressure will be 4. Ant 2 schedules the right half of the DDG first, and then the left half. This frees up a register, leading to a register pressure of only 3 after instructions F, A, and B are scheduled. Since Ant 2 produced the schedule with the lowest peak register pressure in pass 1, we will take this schedule and insert stalls in order to satisfy the latency constraints. So you can see this schedule on the right is the same as this ILP pass initial schedule on the left, but there are now stalls inserted. The ants in this pass will try to maintain this lowest peak register pressure of 3, but find the shortest schedule they can at this PRP. One thing to note about the schedule that Ant 2 constructs is that we insert stalls for different reasons. If you take a look at cycle 4, we could choose to schedule instruction C because it has no dependencies. But we choose not to because this would increase the register pressure to 4, violating our RP constraint. We refer to a stall inserted in this way as an optional stall because we could choose to schedule the stall or an instruction. If you take a look at cycle 8, the only 2 instructions remaining to be scheduled are F and G. However, G cannot be scheduled because it is dependent on F, and F cannot be scheduled because it is waiting for C to finish executing. Because there is no other choice but to insert this stall, we refer to it as a necessary stall. Before we go into the optimizations we made to our algorithm, I'd like to briefly touch on some GPU computing concepts. For our GPU, memory accesses are slow, they're high bandwidth but high latency, so we need to be careful with how we allocate and access memory. On the GPU, the entire collection of threads is referred to as the grid. The grid is made up of 1 or more blocks, which will be made up of 1 or more wavefronts in AMD terminology, or warps in NVIDIA terminology. Lastly, those wavefronts will be made up of 32 or 64 threads, depending on the GPU architecture. These wavefronts are executed in lockstep using single instruction multiple thread execution. Lastly, I would just like to mention that when I talk about memory coalescing and thread divergence in these upcoming slides, these are GPU-specific terms. First, I'll talk about the memory optimizations we made to improve the performance of our parallel ACO code. As I mentioned previously, memory accesses are slow, so we need to be careful about how we allocate our data. We basically always prefer arrays because they're contiguous in memory and they don't involve as many pointers and dereferences as linked lists. Memory coalescing is a GPU programming technique used to minimize the number of loads you need in order to access your data. To take advantage of memory coalescing, we require sequential, dense, and aligned memory accesses, which arrays lend themselves to very well. This should allow one thread to access data next to another thread within that same wavefront at any instance in time, minimizing the number of loads required. Another important consideration was to avoid allocating memory dynamically on the GPU. We initialized all of our objects on the CPU and then copied the data over to the GPU before beginning ACO. While doing this, we also tried to batch together as many mallocs as we could of the same data type, leading to fewer calls to the memory API, which are expensive. This was the most impactful optimization we made in terms of saving compile time. Next, I'll go over the optimizations we made to reduce thread divergence. Thread divergence occurs when threads in a wavefront take different execution paths. Because wavefronts are executed in lockstep, if different threads within a wavefront take different branches, then some threads will be waiting idle while the wavefront executes a branch. All branches will execute sequentially, reducing the usefulness of the parallel power of the GPU. This will occur with if-then statements, where we'll execute both branches, or if we are in a loop, the wavefront will need to iterate over the loop the maximum number of times as any thread within that wavefront. In our algorithm, divergence could potentially occur in 3 main parts. When selecting the best schedule, divergence is minimized because we use a parallel reduction, which is a reasonably efficient algorithm to minimize divergence. It's also minimal while we update the pheromone table, as we can easily assign one column in the pheromone table to a thread, meaning at most, some ants will do one extra iteration of a loop. So, in our algorithm, divergence is most likely to occur while actually constructing the schedules. One place it's likely to occur while constructing the schedules is when making the decision to explore versus exploit. Because ACO has randomness built into it, that necessitates that we make different choices, which could lead to selecting different branches. We minimize this by making the decision to explore versus exploit at a wavefront level. One important note is that you do need to ensure that you're still generating different results in each thread. In our case, even though each thread within a wavefront is making the same decision to explore at the same time, we generate a different random number for each thread, so they will explore to different instructions. Additionally, when exploiting, the maximum scoring instruction is based off of the schedule so far, which will be different as long as the ant has explored before. Another place where divergence is likely to occur is in our main loop. We schedule one cycle at a time, so if we are not careful, we'll need to iterate over this loop as many times as our longest schedule. We implemented two ideas to combat this. The first is to only have a portion of blocks insert optional stalls. As we mentioned previously, we can choose to insert optional stalls to make a schedule longer in order to reduce register pressure. If we can group these longer schedules together within the same wavefront, then that should minimize the disparity between the minimum and maximum length schedule within that wavefront. Additionally, we can terminate all other ants in a wavefront once one ant has finished. As mentioned previously, only the iteration winner schedule is used to update the pheromone table as well as compare to the global best. As such, all other schedules are unused and do not need to finish construction. Because we schedule cycle by cycle, once one schedule has finished constructing and has not violated the register pressure constraint, then all other schedules within that wavefront will necessarily be at least as long as the ant that finished, so they cannot be the iteration winner and they can safely be terminated. Next, I will go over our experimental results. Here's some information on the machine that we use to run our tests. These tests were run using ROCm in the LLVM15 compiler on the AMD GPU. The micro benchmarks that we ran are for ROCprim, which is a library of primitives used on the GPU. We ran our algorithm with 11,520 ants, and we use AMD's scheduler to construct the initial schedule going into pass 1, as well as the guiding heuristic for both passes. Near the beginning, I mentioned that ACO continues for a certain number of iterations without improvement, then it terminates. This termination condition is based on the number of instructions that are in the region we are scheduling. Between 1 and 49 instructions, we will continue until one iteration without improvement. 50 to 99 is 2 iterations, and 100 instructions or greater is 3 iterations without improvement. There were 341 benchmarks that we ran, consisting of about 182,000 regions. We ran ACO on about 2,000 regions in Pass 1 and 12,000 regions in Pass 2. We had an overall improvement of 5.5% in schedule length and 0.66% improvement in occupancy compared to AMD's scheduler. I would also like to mention that small aggregate improvements can still lead to large execution time improvements if the region being scheduled is hot. For our execution time results, this graph shows the 20 most significantly impacted benchmarks. We defined a benchmark as significantly impacted by looking at the difference between ACO and AMD's execution times, and we called them significant if the difference between them was greater than 1%. As you can see, there are no regressions greater than 1%. The largest was 0.7%. The maximum improvement was 74%, and the geometric mean improvement of these 20 benchmarks was 13.2%. These graphs show how much faster it was to schedule each region on the GPU compared to the CPU in Pass 1 on the left and Pass 2 on the right. The blue represents the smallest regions, 1 to 49, which had minimal speedup. However, the medium and larger regions had more significant speedup, with the highest speedup ratio being 27 times in a region in Pass 2. It took 840 seconds to compile these benchmarks with stock LLVM and AMD's scheduler. Compiling with our sequential ACO on CPU took 46% longer than compiling with AMD's scheduler, while parallel ACO on the GPU was only 15% longer. So, we believe that our results show that GPU instruction scheduling can work. We can schedule up to 27 times faster on the GPU compared to ACO on the CPU, and doing so saves about 21% compile time. This got us up to 74% improved execution throughput compared to AMD's scheduler. Since the publishing of this paper, we've been working to improve our algorithm. In the version of our algorithm as presented in this talk and in our paper, we always select the schedule with the highest occupancy. In practice, this is the better decision most of the time, but not all the time. Sometimes it's better to select a schedule that has worse occupancy, but significantly shorter schedule length. Since we're already generating all of these schedules with different ants, we're trying to make better use of them by storing the shortest schedule at multiple occupancy levels. Then, by using some cost function, we intelligently select the best group of schedules at a given occupancy, and hopefully get the best execution time performance by doing so. We're still working on tuning this cost function. As for the future impact of our paper, we believe that our work shows that the GPU can be used to parallelize a compute-intensive compiler optimization, one that's normally done with simpler heuristic solutions. We hope that researchers are encouraged to do so with other compute-intensive compiler optimizations as well. We think, especially for search-based algorithms, the GPU's massive parallel computing power can be used to construct and explore many possible solutions, and the quality of that solution can be evaluated based on a cost function. Thank you for listening to my presentation. Are there any questions?
I have a question. Um, do you anticipate any challenges or limitations when applying these techniques to larger, more complex compiler problems in the future?
I would need to think about that. I mean, at least one thing is you need to find the right problem for it. Not all problems are built to construct a bunch of solutions in parallel. Finding the right amount of work to do on the CPU and on the GPU is definitely important. So I think selecting the right problem and structuring the problem is definitely important. Another issue is just that sometimes you put in work to create these to create more solutions, but selecting the best one, as in our problem, was definitely a difficult problem, trying to figure out which actually is the best solution based on what we might know at compile time, but then at execution time, it's different. So I think a lot of those same issues would apply to other optimizations as well. I'm not sure if that answers your question.
Yes, thank you. We've got two questions over there. Three, actually.
Um, so okay, hi. Thanks for the talk. I was wondering, so you treat the question of like register pressure and then sort of latency separately, and you insert all of these stalls. I was like later, and you optimize for the lowest amount of register pressure. I was wondering if there are cases when you actually are okay with like settling for a little bit more register pressure, but it requires a little bit less stalling. So like the end-to-end runtime is less. Yeah.
Yeah, so that's what we're trying to work on with what I mentioned there. Our current work in progress is not always selecting the best schedule in terms of occupancy. It's difficult to find the balance because it seems like the majority of cases selecting the schedule with lower register pressure is better, but definitely not all cases. And so sometimes that might be a function of whether it's significantly shorter schedule length, or maybe we can look at some metrics like how is memory used, what is the pattern of memory accesses, which isn't exactly contained in register pressure or the schedule length. So there are some factors that definitely make occupancy not the highest priority. So that is something that we're currently looking into, is trying to find what's an intelligent way to determine that at compile time. We can artificially choose to schedule for different occupancies, and then afterwards look at the execution time results and see okay, this lower occupancy is actually better, but the main difficulty is in determining how do we know that at compile time. And so that's what we're currently trying to figure out.
I guess also is a little bit question about like how your search space would explode if you were to like co-optimize these, and whether you have like intuition about how your compile time will grow. Like if you're executing programs, then this necessarily needs to be like an offline, like runs for maybe hours technique. But if you combine them, do you have an intuition about how your compile time will scale?
Well, so in our case, our compile time is limited not necessarily by the solution space, but based on the size of the region and then how many ants and how many iterations without improvement that we do. So the complexity of our ACO algorithm should be roughly n squared, because it's based off, as I mentioned, we schedule every one cycle at a time. So it's the length of the schedule, and then during the schedule, we need to loop through the ready list, which will be limited by the number of instructions in the region. So that's, length of schedule times n. And so that will increase the compile time to some extent, but optimizing for those multiple objectives will be more so limited by that, as well as how many iterations we're doing. So we get to control that a little bit, but then obviously the trade-off is the less time we're putting into finding better solutions, then we don't necessarily get as good of execution time results.
Hi. Thanks for the great talk. This is a really cool project. I was curious, sort of zooming out to like more speculative implications for programming language design. I was actually curious, based on your experience implementing this in RockM and sort of with the like RockM like thread level programming model. I'm curious if you think that felt like the right programming model, or your ideal programming model for implementing these kind of like fairly complicated search procedures on GPUs, or if maybe in the future like some kind of DSLs or like alternative GPU programming models might be more conducive in your view to implementing these kinds of techniques to run efficiently.
I don't know if I have a good answer to that. That's not something I've thought of. I don't know if any of my co-authors that are here, if Dr. Muyan.
Yeah, maybe I can chip in. So actually, we started this project with programming everything in CUDA. However, our target GPU was an AMD GPU. So that's why we switched to RockM. When we compared the two between CUDA and RockM is like less mature language, and it has less documentation and I guess library support, but still it worked for us because we wanted to target an AMD GPU for a specific reason, that it has the open compiler source with MVCC. We don't have that option, so that's why we couldn't target NVIDIA GPUs, and we couldn't use CUDA. But I think RockM was pretty good. But one of our future goals is targeting an NVIDIA GPU by collaborating with NVIDIA. So then we might go back to CUDA. Thank you.
And are there any maybe like more speculative like different abstractions for how you would program a GPU that could make expressing to be clear, specifically like the like compiler, like search process side of this, like implementing that code? If is there anything on your wish list for like features of like GPU programming systems that you think could have made that easier?
Yeah, I think there could be a couple built-in libraries. If it was available for us, it would be easier for us to use. So I think a graph-based approach is a difficult one to use on GPUs because of the way that they operate. So we are aware of some graph libraries that can be used to accelerate graph-related algorithms like the one that we are using, but they were available under CUDA. So I'm not aware of any other alternative one in RockM, so we didn't get to play with it. But because there is graph involved in this project, I think that kind of a library could have helped us to better programming.
Cool. Thank you.
Sure.
I just had a quick comment. So you were talking about like using like an open source compiler, which makes sense. So I just like looked it up. So like NVIDIA also has like their open GPU driver. I know it might not be like like the best kernel driver out there, but like that would also be cool because I'm just thinking that if you can like use CUDA graphs, which is like the NVIDIA graph technology with this stuff, that would be like really interesting. But yeah, cool stuff. Thanks.
Any more question from the audience? Zoom?
I have one more, which is, did you look at the assembly and see anything like interesting? Like, was there any noticeable, maybe higher level pattern in the programs that got a lot of speed up?
I would need to. I'm not sure if there's anything in particular that we noticed. I think a lot of the improvements that we got would just be just getting better occupancy or schedule length significantly better than AMD. I don't remember there being any particular secret hidden patterns. I think it's just a matter of the fact that we're using a more intelligent search algorithm that is putting more effort into it. So sometimes it's going to find things that the heuristic solution will just miss.
Thank you. Do we have any other audience questions? All right then. Thank you very much.
All right, thank you.